Right, we're going to solve this differential equation. There's really two ways you can go about this. One is to use the Wronskians and build out your solution that way. So you would solve the left side equals to 0 for your complementary solution and then compute Wronskians and go from there. The problem with that approach is that when you try to find U1 and U2, you end up with some really nasty integration by parts that's by hand really tedious. It's almost disheartening at one point because you work out one really nasty one and then you have to do it again and then again to get it to work. So pretty difficult to do that one directly by hand. The Laplace though is not that bad. So let's take the Laplace of this thing. We're going to take the Laplace of both sides. I'm imagining the Laplace of my solution x of t. I usually write that as f of s. So taking the Laplace of the left, let's just write it out here. We get the Laplace of this guy. So that means I'm going to have a s squared f of s. Now, I don't have any initial conditions, so I'm going to let x of 0 be c1 and x prime of 0 be c2. That gives me a c1s minus c2 plus 7 Laplace of x is f of s there. So I'm using linearity there to break this thing up. This plus is showing up right there using the linearity of the Laplace transformation. On the other side, I'm viewing this e to the 3t as a shift on the Laplace of t. So the Laplace of t, I know that t goes to 1 over s squared, and then I'm going to shift that with 3. So this is going to end up being 1 over s minus 3 all squared. So that's where we are. We're going to move these two terms across the equal sign and factor. So I'm going to have f of s times s squared plus 7 is 1 over s minus 3 squared plus c1s plus c2. That's a plus there. And then I'm going to divide, and so I end up with f of s equals 1 over s minus 3 squared, s squared plus 7, plus c1s over s squared plus 7, plus c2 over s squared plus 7. Okay. So that's where we get. So now we want to try to go backwards now and figure out what our original function is by taking the inverse Laplace of this guy. And we're going to need to do partial fraction decomposition on this term. For time's sake, I'm just going to go ahead and write that down. But of course, you should be in a position to work that out by hand if need be. Here's what it becomes. It becomes 1 over 16 s minus 3 all squared minus 3 over 128 times an s minus 3 plus 1 over 128 s squared plus 7 plus 3s over 128 s squared plus 7. That's the partial fraction decomposition of just the term on the left there. So now I've got to squeeze the original the other terms in there. So we'll kind of write those small c1s over s squared plus 7 plus a c2 over s squared plus 7. Okay. So we could try and combine some of these things. I almost feel like it's easier, and I think you'll see why, to just inverse Laplace them one by one, and then we're going to see some things that combine in the end. But there are different ways to do this. All right, so now we're in a position to try and go backwards. And so when we do, hopefully you recognize this guy. When we just took the Laplace transformation of t e to the 3t, we got 1 over s minus 3 all squared. So that one is pretty easy. We're going to get a 1 over 16th times t e to the 3t, so 1 down. Hopefully you recognize this s1 over s minus 3 here. That's just, we'll carry out the constant, so minus 3, 128 e to the 3t. That's that one. And then now we're going to start working on these guys. So I am going to pay real close attention to my constants here, but as we're going to see in a minute, even if you don't, you can still, these C1s and C2s are going to swallow up some things. But let's get it exactly right. So this you should recognize as a sine but I need a square root of 7 sitting up there. I don't have it, so I'm going to go ahead and write it as 1 over 128 root 7, and then I'm imagining putting a root 7 upstairs to cancel those out, and that lets me view this thing as the sine. So this becomes what? The sine of square root of 7t. On a really similar note for this one, this is a cosine, so I'm going to get a 3 over 128 root 7 times the cosine of root 7t. Similarly here, this is another cosine. I'm going to get plus c1 over root 7 cosine of root 7t. Oh man, I'm going to have to slide all of this down. It's tight here. And then finally, I'll get a c2 over root 7 sine of root 7t. Okay, so now we can start to think about our solution here. So this c1, I can imagine swallowing up this constant. And this c2 swallows up that constant. And I've got a cosine of root 7t, cosine of root 7t, arbitrary constant. So adding something to an arbitrary constant gets swallowed up as well. So I can combine, let me just use a different color here. I can combine these two, and I can combine these two, and I'll mark my different c's just so you can see what's happening here. But in the end, we get 1 over 16 t e to the 3t minus 3 over 128 e to the 3t. Let's do the sign first. We're going to get a c2. I'll call it like a c2 prime if you want. It's not a derivative. It's just a different c2. I don't really like the prime, actually. Let's get rid of it. It's a different c2 now. It's different because I'm swallowing up the root 7 and I'm adding this thing here. But it's an arbitrary constant, so you can undo all of that and get the same thing. So I end up with c2 sine of root 7t plus c1 cosine of root 7t. And maybe I should have switched the order here so that I had a c1, c2, but it doesn't really matter. That's it. That's how you solve it using Laplace. Oh, I guess I never wrote down x of t. There we go. That's it. Now we're done. And if you had initial conditions right, then you'd be able to get those values exact.